All right, I'm having a lot of trouble getting these videos to save, so this is like my third try. There's a video example from the text if you have access to those video examples, VE 1.1, and it's the authors do a beautiful job of solving this circuit. And it probably looks like a made-up circuit. Towards the end of this video, I'll go through and show you a case where actually this is not a made-up circuit at all. Before you know it, in a few months, a month or so, we'll be doing something like this for a reasonable reason. So we might have a couple of resistors, R2, which is 2K ohms, and R1, which is 5K ohms. And it's fed by a 3-volt source. R2 is fed by a 2-volt source. We've got to call that V2, call this V1. And then we've got a resistor down here, R3, which is 1K. And the authors do a wonderful job of solving this circuit. I would like to know, we want to know that voltage, V3, that use the mesh and node voltage methods and go through and just make it look like it's wonderful and easy. And it is, but those methods really don't give you good insight into what's going on. And they don't really represent the real circuit. And I just think those methods are hard to reproduce in the future. Oops, that's our I1 and I3. So in addition to knowing that voltage on node 3, I would like to know those currents through each of those resistors. And I think that you should try consider solving circuits like this through Thevenin, and that's what this example is about, making Thevenin and Norton conversions, transformations, so that it becomes easier to do. And if you think about this and look at it, actually, this is already a Thevenin circuit, and this is already a Thevenin circuit. And what I'll always tell you is when you don't know what to do with a circuit, if you got Thevenin, convert it to Norton. So I could redraw this right now as we've got this voltage source V2, and it's also connected over here to another voltage source R1, and then they are feeding that resistor R3. So let me put those numbers in. So we got R2 is up here, 2K, and we've got R1 that equals 5K. Why does it disappear sometimes? And we've got R3, which is 1K, and we've got V1, which is 3 volts, and V2, which is 2 volts. And we're looking for the currents, but we're also looking for this voltage here, V3. Once we can find that voltage, we've got everything. Well, the thing to do when I see that, like I said, is when you don't know what to do, convert Thevenins to Nortons. So if we do that, if I will convert those to Nortons, let's just do it over here. Wonder how big I can make this thing. So if we look at the R2 side, V2 side, that converts is 2 over 2000. So 2 volts over 2000, that equals 1 milliamp. So we have a current source with 1 milliamp. And there's a resistance that disappeared on me. So it's going to have to tell me why this stuff disappears sometimes. That'll stay. And then we have, it's going to go away. At least I can tell now by the color when it's going to go away. And we're going to find this other current source. That's a value of 3 volts over 5,000, which is 0.6 milliamps. 3 over 5,000. So we've got those currents, and then we also have one more resistance in there, which I didn't leave enough room for. So I'll just write in the numbers. We've got R2, we've got R1, and we've got R3. And we're still actually looking for this voltage right here at the top there of V3. Beats me why some of that stuff doesn't want to show up. So now that you see it like that, it's like, well, okay, I know what to do with a circuit that has 2 Nortons, 2 current sources, and 3 resistors. Those are just in parallel, and so the currents add up. So we get a single current source, which is drawn. Try that again. Single current source, which is the sum of those. So 1 milliamp plus 0.6. And then a single resistor, which is the equivalent resistance, which is R1 parallel with R2, parallel with R3. And that, of course, is works out to 588 ohms. All these little dots. That's what those work out to. Now, we can find we can convert that back to a Thevenin, and in fact, at the top of this this voltage here is still actually V3. So we can find that if we go back to the other way. So now we have V3 is equal to that equivalent voltage. It's 0.0016 times 588, which is equal to 0.94. Let's just go with 1 volts. And so we'd have a Thevenin source that looks like that. 588 ohms. And 0.941 volts. And now we know that V3 is equal to 0.941 volts. From that solution we just did. And hopefully that didn't seem too terribly hard. Now, that's easy to find V3 by that means, but we don't actually know these currents. So I2 is not the same as the current through here, and I1 is not the same as the current through here. This current and this current are not the same as those 2 currents. So as nice as that would be, it's not quite that easy. What we need to, though, is now that we know V3 and we know V1 or V2 and we know V1, we can subtract these 2 and knowing the resistance, find that current, and subtract these 2 and knowing this resistance, find that current, and then we're on our way. So We'll do that. So well, we know B3, so we can find I3. So I3 would be V3 over R3. So it's 0.941 volts over 1,000 ohms, or 0.941 milliamps. I think that's amps, not milliamps. 941 milliamps, I think. If that's the voltage, and that's the, yeah, so, or no, it is 0.941 milliamps. That's 1,000 ohms. Okay, and I1 would be the difference from V1, which is 3 volts, divided by that resistance, 5,000, and that equals 0. Or no, sorry, I need to do 3 minus 0.941. That's just what I told you don't do. And that equals 0.412 milliamps. And I2 is equal to 2 volts minus 0.941 divided by that resistance, which is 2K. And that equals about 0.53 milliamps. More rounding than I should. And we could add these two up. Could add these two up and make sure that it checks to that voltage. And they do. 0.412 and 0.53 is about 0.941 milliamps. So I1 plus I2 equals I3, and it does check. And that's a solution. So I'll give you an example. You can work on that right now. And then when you come back, I'll show you a real example. So a real example of a circuit like this that we'll be doing before you know it, although you don't really have to learn, the particulars of what I'm showing you at this point. But this would be a diode circuit. And the way we might solve it, if we were looking for that voltage at that intersection right here, and if we know that we've got some, let's see, we've got 20 volts, and we could have a 6K here and 4.9K. We've got a diode, and we've got some current there, and 4K. Diodes are kind of weird things. They're nonlinear, but we can sort of do a piecewise approximation. And doing those approximations will often say that the voltage across here when it's on is 0.7 when it's on. And we'll explain all that. I'll explain all that in chapter 4 in more detail. But it means that if we called that 0.7 volts, that we could redraw this. We could redraw this like this. I'll draw it with a battery. It's not a battery, it's not a voltage source. It's something that just supplies 0.7 when it's forward biased, which is a strange thing. So at 0.7 volts, we've got 4.9K at 20 volts, 6K, and 4K. And of course, I could redraw this as this other evil-looking circuit that we already did. I could redraw this. Just like this, with 20, 0.7 volts, 4.9K, 4K, 4Ks down here. And 6K, and tell you that I want you to find this voltage right there and find those currents. Well, you could use exactly that same method that we just went through to solve it and solve the circuit. You don't do this, but we'll be doing this kind of thing before you know it. So this circuit that we just did, it may seem and look made up, but it isn't. It's actually a real circuit that is useful and occurs. And this kind of Thevenin to Norton to Thevenin conversion is pretty straightforward. It doesn't take any really hard thinking. Don't have to memorize those weird methods. And I think it gives you some real insight into what the circuit is doing.